I don't think I know you. Okay, now we're recording. Hey, if you missed this recording, there's a bunch of stuff due coming up next week. Talk to me if you need the details. So, yeah, so we want a rigorous argument to establish the validity of a claim. There's all sorts of terminology that goes with this, and I'm kind of curious how much of that we remember from the prep. And so maybe we can play what is this right now? A little bit of Jeopardy going on here. I've got like literally like almost it's like the Brady Bunch in front of me here. So what's a theorem? Oh, okay. So I'll go, Caden. Abraham, I'm going to come to you next. So maybe look at the next word on the list and be ready for it. Okay, so Cadence, what is a theorem, sir?
A mathematical assertion that can be shown to be true.
Solid, nice. Yeah, and theorems are usually really big results. So I would add that to it. So these are big mathematical results. Something you really want to stand out. What's a lemma, Abraham?
A lemma is a lesson supporting theorem helpful in the proof of other results.
Solid. So a lemma is like a little mini result. It's like a building block for a theorem. So we sometimes when we're proving things, if you really have a complicated proof, you will start by proving a lemma. And then you will use that lemma and maybe a couple lemmas. It's a neat word. I always like the word. It's just so odd to prove a theorem. So these are smaller results. These are building blocks. What's a corollary? Joey, what's a corollary? You look like you're thoroughly enthralled with this discussion. I see you looking for it. What's a corollary, my friend?
I believe that would be functions that relate to each other. Correlate.
Ooh, I see. You're winging it. I like it. This is a man who's using some Latin or some Latin skills here to pull it together. Kind of. Tracing, my friend. You're close, Joey. That was good. I appreciate you playing along for sure. Tracing, what's a corollary?
Corollary, I got a theorem proved directly from some other theorem.
Solid. So it correlates, I'll like pull Joey's words in here, correlates to another result, but it's kind of a smaller result that comes from a theorem. It's like, oh, here's a quick result that we can prove. So a corollary follows from a theorem. And then sometimes you get many corollaries from one theorem. Bunch of little special cases. So these are kind of like special cases of a theorem. What is an axiom? Anybody, Yvonne? I guess that, yeah, apparently it's not anybody. I'm just making you do it, I guess.
It's statements that we assume to be true.
Solid. So these are like things we just assume to be true. And, you know, that's a lot of things. So these are accepted facts. Let me give you an example of one we've been using all semester. There's this thing that, so Archimedes, you've heard that name. Archimedes was one of the founders of Western logic. There's actually like a couple types of logic. It wasn't all just in the West. In the East, there are some really interesting logics, but they don't have this law, this axiom. So there's this axiom of the excluded middle. And this is from Aristotle. So we can thank Aristotle for this. And Aristotle founded the logic we started off this class with. And it basically says something can be true or false, and that's it. There's no middle ground. So things are true or false. And then we proceed from there. Now, that sounds, it's like at first glance, it's like, sure, that sounds right. Why is that actually maybe not? Why is there complications with that? Does anybody care to like argue against Archimedes? Because I'm ready for it. Sophia, what do you think? Sorry, this is a tough one. So this is a tough one.
It caught me off guard. I was trying to write down
Okay,
the definition
no,
for
that's cool.
axiom.
Okay, no, that's cool. That's cool. That's cool. All
Oh,
right.
my bad.
I'll get. Does anybody care to step in here with like in life? So just take life. In your life, in your experience, is everything either true or false? No. So I'm getting like a no from Cadence. Cadence, would you mind just sharing your thoughts on that?
I mean, I think that especially with like more complicated thing, there's different ways to interpret, and there's degrees of gray that you can't just make a hard and fast statement of something being true or false.
Yeah. Right. Yeah, exactly. I mean, just look at the state of the United States right now in political discourse, right? We can't even agree on what's true or false. And you might think, well, clearly the stuff I believe is true. But maybe not. Somebody's got a different perspective on it, and therein lies the problem. Of course, we can't like settle it like civilized folks. We have to just be complete assholes to each other. But most things in life, I think, aren't just true or false. Anything that has to do with life itself. So in the East, there's like a whole other branch of logic, not this Aristotelian logic that we accept as true. There's this other logic that allows middle ground. And we're not going to talk about this, but there's a logic, and it's actually formed in early Buddhism and Hinduism. And things can be, instead of just things are false or true, this like you got one or the other, it could be false and true. False and not true. It's not false nor true. It's just all this stuff. So there's like 4 different, not false nor true, and then there's like one more. I'm not getting them all right, but allowing for all the shades that we know exist in life. I'm hearing some odd bubbling. Did someone just say something to me? Someone say Dr. T?
I just joined Dr. T. I was just apologizing for being late.
Oh gosh. Oh no. Wait, who is that?
It's Vincent.
Oh, hey Vincent. Oh yeah, okay, there you are. I'm glad you're here. I was worried about you. So
Yes, sir. Thank you.
no, just great to have you here. Thanks for showing up. Cool. So you know what, Vincent, you're gonna be okay if you miss this first part. It won't affect anything, but there's a bunch of different assignments and stuff you might want to check on.
Okay, cool.
Okay, cool. So let's take a look at a couple really famous theorems. And you might have heard one of these. You might not be familiar with these at all. This first one's Euclid. Euclid wrote the very first textbook in the Western world. It was a book on geometry, and it was proofs of all these geometric facts. And they look so different than the stuff we're used to today because the language was totally equal. Sorry, I was thinking of my next sentence. The language was totally different. When Euclid would say 2 things are the same, he would say they were commensurate, right? So there's like this whole different language barrier to get through. But one of the things Euclid proved is that there are infinitely many prime numbers. I think we already talked about primes. And as a computer scientist, primes are going to be part of your life. So this fact is not obvious at all. I mean, we could start listing them off. Remember when we did this before? They're all the numbers that can't be divided by anything but 1 in themselves. So we had this list. Let me know if I miss one. That'd be pretty poor if I missed one. And so forth and etc. So it seems like they're going to keep on going. But we can't say that for a fact. I can't just go, well, it's obvious. What I need is a solid argument so that the people who use prime numbers, like cryptographers, know there's always another prime number available to use for encoding things. And that's primarily what they're used for in computer science, encoding things. So Euclid proved this. We're not going to go through the proof right now. It doesn't matter to us. But he used what was called a direct proof. Oh no, actually, no, he didn't. Yep, forget that. He proved this shit. He didn't quite use the methods we're using, but they're methods we will talk about eventually in this class. So having that fact known as a truth is really important, and there's no other way but a proof. What about this last one? This is Fermat's last theorem. Has anybody heard of this? No? Okay, so Fairmont, a famous mathematician in the 1800s, was doing just crazy amounts of math. And he had this journal that he was writing all his math in. And at one point he wrote this statement: no three positive integers, a, b, and c, satisfy the equation a to the nth plus b to the nth equals c to the nth for any integer n greater than 2. Now, let's talk about that result. When n equals 2, that's definitely something we can satisfy. Does that equation look familiar? A squared plus b squared equals c squared, right? That is a triangle. That is literally one of the basic laws of a triangle. That if I have a right triangle, a, b, and c, that's the Pythagorean theorem. So way before Fermat, we knew that that was true. And so Fermat was like, well, I wonder if this equation has nice integer solutions, nice whole numbers, a, b, and c, that satisfy it. And you can sit here and you can start trying to figure some out, but you never will. Like this one here has got lots of solutions. I know that 3 squared plus 4 squared is 5 squared. I know that 5 squared plus 12 squared is 13 squared. I know all sorts of those. There's infinitely many. They're called Pythagorean triples. But this equation, or this equation, no one could find any solutions. No one could even find one set of A, B's, and C's that made those true. And so it was like, well, this can't be true. And so in his journal, Fermat said, yeah, you can't solve this thing except in the special case of the Pythagorean theorem. When that exponent is bigger, there's no solutions. And then he wrote, the proof is quite simple, and I've written it in the margins of this book. But that no one ever found the margin of the book where he wrote it. So he left this mystery in 1637. And I wish people would have asked him back then, like, what was the proof? What was the proof? So for 300 plus years, we didn't know if this was true or not. And then in 1997, this guy Wiles, Andrew Wiles, proved that, yep, Fermat's last theorem is true. There are no A, B's, and C's that satisfy these equations, or with A to the 5th, B to the 5th, C to the 5th. There's no solutions that are integers. And he proved this using incredible, like math I don't understand. It's not my specialty. It's incredible math. But he came up with a solid proof that this is true, and it was the first time ever, 350 years later. So there's just a couple dramatic moments from the history of proof. There's more, hopefully, that we'll talk about throughout the semester. But we won't be proving those results. we're going to start off and kind of like work our way into this easily. By the end of the semester, you're going to know a couple of ways to prove things. And more importantly, you're going to know how to understand if a proof is good and how to read it. This isn't a class about proving things, but it's a class about proof awareness, mostly. If you really want to get into proofs, take MT320. That's logic and proof, and you'll become a master of proving things then. And if any of you ever think about doing math as a major or a minor, let me know. Please, let's hook up and talk about that. And we'll get you lined up with a good course of study. So for us, friends, we're going to focus on direct proofs. And a direct proof is that I want to prove a statement like this: if something, then something else. Whoa, what just happened there? Then something else. So P implies Q. If P, then Q. That's all we're going to focus on for this first exam and just this next week or so. So I want to give you some like tips on how to do this. We're going to practice it today. And then that written assignment that I've got up for you, that's you practicing this skill like a number of times. And we'll have Monday. What would be great is if by Monday you could like work on it between now and Monday, and then we get to class and we can talk about how to deal with it and worry about any problems you may or may not be having. Because I want everybody to just smoke it completely. So this got all weird here. But let's talk about how to do a direct proof. So first off, in the upper right-hand corner, I should put this in like big explosion here. Jesus, I hope I spelled believe right. Some words never look right to me. There's this friend. I literally still have to look up the word friend about every 3 weeks just to like know if it's IE or EI. I just can't do it. The IE thing is tough for me. I think I got this. We lost some folks. Where is Sophia? She's still here.
I'm here. I
Yeah,
just
oh.
my camera, my thing froze, so I had to turn off my camera.
Okay, no worries. I'm glad you're here. Cool. And Selena's with you?
Oh, he can't see me. Sorry. Yeah, she's right here.
Okay, awesome. Yeah. Solid. Cool. So first off is, oh, hi. All right. So first thing is, sometimes you don't know if the thing's true or not. And you need to think about it because you don't want to dive in and, it's kind of like you've got this car and the car doesn't run and you're like, well, I better get in and figure out what's wrong with the engine, and sometimes it's just that it's out of gas. Or like if you're in IT support, anybody here do IT support? Some of you must. No, nobody's doing IT support for Regis? No? Oh, Joey, you are? Yeah? No. You're sending me mixed signals, Joey.
I should do it, but I don't even know how to get introduced to that.
Oh, really?
Yeah, I'd be down though. If you know where I can get a job there.
Yeah, let's talk. I mean, I don't have any, I got no power, I don't know people, but I know where you can go. And I'll give you a recommendation. How's that? Yeah, all of you. Let me know if you want to do that. So first off, we have to decide, is this thing worthy of our time in trying to demonstrate it's true? Because you don't want to be knocking your head against the wall trying to prove something that can't be proved. So that's step one, and we'll get into that. Let's just go through the kind of flow first and then try the flow. So once I believe something's true and I want to demonstrate that to someone, what I do is I assume the hypothesis is true, right? So I've got this if something, then something else. I assume this is true. And then from there, I need to understand what it means for that thing to be true. So that's the second part here. So this is the first. Second thing is understand the consequences of that thing being true. And you might have to look up definitions. or equivalent statements that are true, logically equivalent things. But we need to know what we're assuming is true and deeply understand it. Then once I do that, there's this game. Here's what I have is true, and I know it's true. Here's where I want to go. And I need to figure out the links between what I have and what I want. And you might have done this in science classes, like in physics. You've got some equation, you need to show it to say it's this other equation, and you kind of just look to see what the next step is. And it's a little like algebra. Show this thing is this thing. It's very much like that. But that's where the hard work comes in, and that's why you need some practice. How do I link from what I know to what I want to show? And then I do some scratch work, I make little notes, and then I make it pretty. And that's something I'm definitely going to require. I want pretty legible arguments. That means full sentences, right? So a lot of people think math doesn't, you don't have to write in math. You have to write in this kind of math to write pretty full sentences, capitals and periods and shit like that. I don't care if you end in a preposition. I'm not that kind of guy. Like, that's not my wheelhouse, but I want it to make sense and look nice and sound nice. So let's take a look. Let's get into this. I have a claim. If n is an odd integer, so let's talk about what the integers are. We've talked about this a little. So this symbol z stands for the integers, that capital Z. Nice pretty symbol. And it's from the German, it's from a German word that it's escaping me right now. You know, it's something that sounds like Zachton or something. I don't know. It's some Germany word. Zahlen stands for Zahlen. So it's not too Aki. So the integers are the numbers that look like this. They're the whole numbers. There's 0, and then there's the negative numbers. So as I'm reading this claim, I'm in my head going, okay, it's an integer. What does that mean? But more particularly, it's an odd integer. So the odd integers are going to be 1, 3, also -1. We don't often think about negative numbers being odd, but it's going to be every other integer now. So like -3, that's going to be an odd integer. 5, -37. All those are odd integers. So we have a sense of what those are. And so I'm going to write that down. And you might want to, well, you don't really need to, but the little sheet that I have you fill out, not a little sheet, but the Word doc has these exact things in it. So like for each of the things I ask you to prove, I would really like you to fill in these spaces. So like, what are my assumptions? So my assumption is that n is an odd integer. And it's really important. I mean, this isn't busy work. I'm not trying to just get you, this isn't like a business class. Like I've been told there's a lot of busy work in business classes. I got a guy who does business, but he took a calc class with me and he just wants to keep taking more calc because he's like, we're doing stuff. we're like doing stuff and it's exciting. So n is an odd integer. What does that mean? Well, I could write out a sentence that means n is -1, blah, 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 but I don't know what n is. So I need to pull some more abstract definition out. So at this point, n is an odd integer. I'm going to write here, what does that mean? And so what I'm going to do, I'm going to actually pull this out of here for a second. We need to get a definition. get the mathematical definition. And I'm going to give that to you now. So the definition is this. An integer n is odd if there is, how about this? If n, equals 2 times k plus 1. So this might be the first time you've seen anything quite like this. If n is equal to 2k plus 1 for some integer k. That's what I want you to use for the definition of odd integer. Let's explore that just for a second, make sure that makes sense. So for example, 3 is odd because 3 is equal to 2 times 1 plus 1. So basically, it's like you find the nearest even integer, which is the 2k part, and then add 1 to it. So you find the even underneath it and then bump to the right. What about this one? -7 is odd because -7 equals 2 times, can you fill in the blank for me there, please? Why is -7 odd? What goes in the blank? What is the k for us? Okay, I'll get you in a second, Cadence. Absolutely, got you in the queue. Just want to give everybody a second. I think Sophia and Selena just figured it out. Yeah, okay, good.
It took me a second, but Selena got it. So I was like,
Solid. Is anybody like really struggling with this? Like not quite sure how to go? Right. Cadence, please, what is the k here?
-4.
-4, absolutely. Because you have to go to the left of your number and then add 1. So 2 times -4 plus 1. That's why -7 is odd, because it's twice some other integer plus 1. That's going to be our definition. Let's get another definition out here. See if you can finish this for me. Because you'll need this for your homework. An integer n is even if, can you fill in the blank? What is the rest of that sentence? I kind of want somebody else to help me here, too. Kyle, are you feeling like you might have this one? You got it? Would you mind? Do you feel comfortable sharing that? Thank you.
All right, so I just said an integer n is even if n equals k divided by 2.
Ooh, that's really close, but what if I said, but what about, so you're saying n if k over 2, like, is this what you're saying, like this? Like this?
Yeah.
So what if K was 14? What would N be?
That'd be 7. I guess
Yeah.
that doesn't work for all
It's
cases.
cool. But you're thinking right. You're totally thinking right. So let's just keep this. Let's do you mind if we talk just a little bit more about this? Yeah.
Yeah, sure.
Beautiful. So look at the way that top one is. It says N equals 2K plus 1, and that gets us an odd. So how could we modify that without going to division or anything to get us to just an even? And it's close to what you were saying, but it's not division.
Two K plus 2.
Oh, that's hella good. I like it. That would work. That would freaking work, but we can make it a little simpler and just go 2K. But your
Oh,
definition,
yeah,
you gave a totally legit definition. Beautiful. And your reasoning, I can see it. You're like, oh, add 1 to an odd and you get an even, right? That was kind of, I think, what you were thinking.
Yeah,
Yeah.
along the
But-
lines.
Yeah, along the lines. But you can also subtract 1, right? And so then you lose that plus 1. But beautiful. Thank you. Many thanks, sir. So an integer is even if N is equal to 2K. It's just twice something else for some integer K. All right, these are primal definitions. We're going to need a bunch today and for the next week. Any questions at all right now? You feeling? Are you feeling? Everybody feeling like they're coming along and this is clear? You might not know where we're going, but let me know if you're not clear. Okay, so holy shit, that's a lot of writing that I don't have room here for anything else. So I'm going to skip ahead. Well, no, I'll just erase this. Is that okay? Can I erase here? Are we all okay with that? Yeah, thumbs up. Yeah, okay. Because it's being recorded. Yes, so we're good to go. So that was the, gotta look at what was my little flow that I wanted to do. I gotta go look at the assignment now. So wait, but that was the assumptions, right? Okay, all right, got it. Assumptions. And so N is odd. So N equals 2 times K plus 1 for some integer K. Now I have a handle. Now I have a formula. And getting that is going to make the whole rest of this flow for some integer K. What's the next thing that I had up? Did anybody write down the next thing? I can't even find the dang. Oh, wait, let me find my Word doc. Oh, there it is. Oh, there it is. Cool. Want to show. So I've got my assumptions. I've looked up a definition and I've got a better handle on what that means so I can use it. I want to show that N squared is odd. And then, so like, what does that mean? What does that mean? i.e., I want to show that N squared equals what? What do you think, Daniela? Don't get too deep, just like we want to show it's odd. What does it mean to show something's odd? That's all I'm asking.
Oh, so like the numbers multiplied, like equal or not? I don't know.
Yeah, it's okay. So what does it mean? So what does it mean if I said, hey, Selena, this number is odd, what does our definition say?
It's not divisible by 2.
That's
Well, if you
also true.
divide it by if you divide it by 2, it's not a whole number.
Yes, yes, exactly. And we can be super precise and just say, we can use this definition. Well, shit, I erased it. This definition right here, right? So when you see odd, think this immediately. So in other words, n squared is equal to twice some, and let's just write this out, some integer. I'm going to write this in English. Some integer plus 1. So I have to show that n squared has this form. In other words, i.e., n squared has this form. And once I've done that, I'm satisfying the definition. In other words, and I was going to, let's get a little more technical, that n squared equals 2 times L plus 1 for some integer L. And I have to use a different one than I did up above because I don't know that they're the same. So I have to use a different letter here. So that's what I want to show. And if I can demonstrate that, I'm solid. I got the proof. So let me stop and ask and take a minute. Does this make sense? Because the next part is we're going to find the reasons between the assumptions and the want to show. We're going to make a flow that gets us there. All right, groovy. I'm going to move. So, oh, I should have left some room here. Let's just go here. So we are trying to prove, let me just get it out here for scratch work, that if n is odd, n squared is odd. That's basically what we're trying to show. Our assumption was that n is odd, which said n is equal to 2k plus 1 for some integer k. And we want to show, so I'll do WTS, want to show n squared is odd. That means that n squared is equal to 2 times some integer L plus 1 for some integer L. All right, so now here's my scratch work. If you're not used to doing scratch work, please do it on these proofs, just so like you do this little stuff off to the side and then you make it look magical and easy. You do it the hard way. So we know, you might not be writing all this stuff, but I'm writing it for you, that n is equal to 2k plus 1. So now I'm just going to square n. So n squared looks like this. Now let's play a little game and you can just answer privately. I don't know if I want to know, but is this true or false? Don't write this down. Is that what I need to do there? Is that true or false? Yvonne, yeah, Yvonne's not holding back. That's a stinker. That's what you wish it was. That's what everybody wishes it was, because life would be so smooth. But that is not correct. So good job, Yvonne. Good call, my friend. We gotta multiply that thing out. So that means this is 2k plus 1 times 2k plus 1. What's the rule I use? It's a word. It's a 4-letter word that starts with F. Yeah, what? I said, wait, are you saying, what are you saying, Sophia?
Foil.
Okay. That's right.
I wasn't sure if it was right.
Yeah, no. That's it, foil. So I'm gonna foil this shit out. So that means first, and you're supposed to kind of like know this when we get here. So let's at least talk. So first times first is 2k times 2k. That's the first. Plus the outer is 2k times 1. So I'm multiplying these outer two things together. Plus the inner, that's the 1 times the 2k. Plus the L, that's the last two multiplied together. So plus 1 times 1. And then simplify. Take a moment and please simplify that. If this is like cake for you, I'm gonna ask you, can you take the proof home? We're gonna do it together. But can you take this the rest of the way? So just checking in together. Does that all make sense, what I've done there? Yeah. Yeah. Does anybody need any explanations on any of it? Because I'm so happy to talk about it. There's this word that mathematicians, there's a couple phrases mathematicians use. And clearly, and you'll see those words all over mathematics. It's obvious that, or clearly this is the case. And I hate those words. They're very presumptuous and kind of condescending. So I try to avoid them. I don't think anything's obvious necessarily. Is this making sense? All right, cool. So now look at what I need to show. So I've got some stuff here. Man, that doesn't quite look like what I want to show. What I need is, I'm going to put a little question mark here, is how is this equal to 2 times some integer plus 1? Because if I can make it look like that, and this is an integer in here, then I'm done and I've demonstrated what I need to demonstrate. What could go in those parentheses? So I've got 4k squared plus 4k plus 1. I want to rewrite that as twice something plus 1. What could that something be here? What is that something? Yvonne, are you feeling like you might know? That's okay. That's cool. No pressure at all. But Abraham might know. No, you were doing the bop. Yeah, you were like doing your bopping thing. I was like, he's got it. He's got it for sure. Okay, no. Can anybody help me out here? Cadence? Yes.
It would be 2k squared plus 2k, right?
That is right. So check it out. Look at that. So, like you look at what you need and you think, well, what would have to be in there? Does anyone have trouble seeing that 2 times 2k squared plus 2k is the same thing as 4k squared plus 4k, right? That's you distribute that 2. So it's kind of like just factored a 2 out of those first 2 terms. So now check it out. Why is this an integer? Is that an integer? So here's the next question, right? Because it has to be 2 times some integer plus 1. So let's just make a little note over here. Why is 2k squared plus 2k an integer? Cadence, let's go.
We've stated that k was an integer and we are only multiplying it by itself or another integer.
Solid. So check that out. That's beautiful. Thank you. We know that k is an integer. And when you multiply integers together, you just get other integers. And when you add integers together, you just get other integers. So let's get some fancy lingo so that you can say this, because you're going to need to say this. So let me just kind of like copy this over. So here's where we're at. And then we said, well, that's this. I'm just copying what we already have. And then I would write here, 2k squared plus 2k is an integer because k is an integer by assumption. K is assumed to be an integer. And check this out. Here's some fancy lingo. And the integers are closed under multiplication and addition. That's the sophisticated way to say that. That's like the technical way. And the integers, and you're gonna need to say that in almost all these things that I've given you to do, are closed under multiplication and addition. That means if you go, I'm sorry, go ahead, please.
Sorry, I was just going to ask you to explain what that meant more.
Absolutely. So that means that, i.e., if I take an integer times an integer, I get an integer. Pretty much what you said. So that's closed under multiplication. So don't try to read too much into it. It's just really a fancy way of saying exactly what you said, Cadence, that if I multiply 2 whole things together, I get a whole thing. And that if I take an integer plus an integer, or plus or minus even, right? That also works. Plus or minus an integer, that equals an integer as well. So this is closed under addition. Are the integers closed under division? If I take 2 integers and I divide them, do I always get an integer? No, I do not, right? I get like fractional things. So the integers are not closed under division. I mean, take 2 examples. Here's 2 and here's 3. That's 2/3, right? That's like 0.6 repeating. That's not an integer. But if I multiply 2 together or I add 2 together, I'm golden. I just get integers all day long, closed under those 2 things. All right, so there's a lot happening today. The class, we went out to sea, right? We're heading out on our cruise. Can I answer any more questions at all about this? We're going to keep going and I'll keep explaining. All right, So let me, I wish I could just cut and I bet what are those? What's that? Well, obviously I don't know, and I'll figure it out on somebody else's time, not yours. So I'll work with this. So okay, so here what we got. So we got n squared equals 2 times, and then we say if we let L, because remember where we were shooting, let's go back to the beginning. I want to show, come back to the want to show. What did I want to show? That n squared equaled 2 times some integer L. And I kind of want to stick to what I said, and I wrote myself a little contract. So I'm going to stick to that. So if we let L equal, woo, that is a red integer. Oh, screw it. We'll just go Christmas on this thing. Sorry, kind of weird, little abrasive. Then L is an integer because the integers are closed under multiplication and addition. So n squared, I gotta stop this red, I hate it. 2L plus 1 for some integer L. And that's kind of my proof. So I've done, like, your scratch work probably won't be this detailed, but I'm making it detailed so that we can understand what's happening here. So watch this. I'm going to put this all together now. Here's what the final product. So that's the end of the scratch. Woo, stop it. No more red. Final product's going to look like this. Proof. Assume n is an odd integer. Then, look how I'm just keeping a flow here. I'm just writing sentences. Then n equals 2k plus 1 for some integer k. Now watch how I'm tucking things under and hiding them until I want to reveal them. Things that I understand already. That means, and you don't have to use the words I'm using. You can use all sorts of other transitions. But if you want to use these, please go ahead. That means that n squared is equal to 2k plus 1 squared equals, and then here's where you did this scratch work and you just like whip it out and you go, oh, that's this. So I'm hiding some of the details from my scratch work to make this elegant. And that is equal, and then here I could even just put underneath that, so that is equal to 2 times 2k squared plus 2k plus 1. So if we let L equal 2k squared plus 2k, then n squared equals 2L plus 1, where L is an integer. And then here I would put a little note, I'll put parentheses, because integers are closed. Under times and plus. And I've shown that n squared is that form, so n is odd. Thus, or hence, or so, n squared is odd. And that's the elegant proof. And it's not always going to take this long. Like that took a long time. That was like 30, something minutes for us to talk through that, but that's because there's a lot of other stuff going on. So we're going to practice this before you leave today. We're going to do something a little bit different. Please let me know if there's anything right now that you just like a burning question or something that's not making sense. Okay, your turn. Prove. Let's see, what do I got here? I got a couple of things for us to prove. Let me look. Oh, wait, I think I got, oh, go back because I got all this shit back here. Ooh, let's do this one. Cool. So I didn't finish the claim. What should be in the blank? So add a couple odd integers together. What do you think the general result is? The sum of two odd integers is blank.
Even?
Yeah, indeed. Who said that? Is that Trayson? Yeah.
Yeah.
Beautiful. Yeah, absolutely. So even is the answer there. And to you, what you do is you do a little scratch work. You're like, okay, what's 7 plus 5? Well, that's 12. What's negative 9 plus 15? Well, that's 6. And so I convinced myself that, oh, okay. Yeah, I think even is the way to go here. And it's just a few cases I look at, but now I have to show it in general. So the proof, so let's just do an outline. Do not have to write anything elegant. So assumption. We've got two integers. And let me get you started here. Assume m and n are odd integers. So now I'm going to walk everybody through this kind of slowly, but if you feel like you're ready to run, run. What does it mean to be an odd integer? Now you got two of them. Somebody help us out here. Cadence, what do you think?
M and N both equal 2K plus 1.
Are they necessarily the same?
No, but they both would equal 2K plus 1. So would it be like 2K plus 1 and 2 L plus 1?
That's it. So
Okay.
yes, exactly. We have to allow for the most generality here. So that's a little subtlety. So we're going to assume that M equals 2K plus 1 and that N isn't necessarily the same. So I'm using L. You can use any letter you want there. It's all good. So K, an integer, and L, an integer. So now, just make the move, friends. What is, and we're not going to write, we don't have time to do the whole formal proof, but what is M plus N and why is it even? Remember what it means to be even. I'll put it over here so you've got it in front of you. I'll try to use some. Okay, so Cadence has helped us a lot today. I'm gonna let Cadence keep chilling there. Can somebody help me on the next move? Yes, Sophia, please help me. Beautiful.
Would it be like 2k plus 1 and 2 plus 2l plus 1?
Yep.
And then it simplifies?
Yes.
It would be 2k plus 2l plus 2. And you can factor out the 2.
Oh, so beautiful. Absolutely. So that's just twice k plus l plus 1. And why is this an integer, my friend?
What was that?
Why is this an integer?
That's a great question.
Thanks.
I honestly don't know.
Remember that word closed?
Because it's closed under multiplication and addition.
Yeah. So this is an integer because k and l are integers, and so is 1. And I'm just adding them together. When you add integers together, you get integers back. So this is an integer. Does that make sense? Yeah.
Yeah.
Cool. Because the integers are closed under addition. I don't even have to say multiplication here. So I've shown that m plus n is twice something else. And then I could just kind of like wrap this into a nicer argument. And I would, if I didn't have like 2 minutes left and I wanted to tell you one more thing that'll help you on your assignment. So friends, this recording will be up if like you want to go back and check this out. I'll have it up on YouTube. But let me give you another, because your first problem in that homework set says something like this. So it says prove or disprove. So you'll have to like be careful with that. One of the things I ask you to prove is not true. There's 3 things I ask you to prove. One of them is false. So you'll have to like check out some cases and think about it. But this one says prove for all integers n if n is divisible by 3, then n squared is divisible by 9. That's the first thing I ask you to prove. It looks very similar. And it's kind of like the even, but what this means, let me help you out here. And there's some definitions you need to fill out as well. But if I say, and I'm basically giving you the answer to something here. Definition, an integer n is divisible by 3 if n is equal to 3 times another integer. In other words, i.e., n is a multiple of 3. That's another word. That word you might be more familiar with. It's a multiple of 3. So it looks like the even definition. The even definition just is n is divisible by 2. That's an even number. Divisible by 3 is the multiples of 3. Divisible by 5 is the multiples of 5. Then I ask you to generalize that. So we are out of time. My voice is just about shot. But we've stepped things up a little bit. So what I need you to do, what you need to do for you is check out that assignment and please start on it before Monday. Give it some thought. If you don't, you're just not going to get anything out of the discussion on Monday. And you can see that this is going to be new stuff. These are new skills for a lot of us here. And if they're not new skills, if this is easy, then what I will expect from you is really beautiful proofs. I will expect elegance if I think you think this is easy. All right. So my friends, thanks for being here. It's been a pleasure, and I will see you. I can't imagine why I wouldn't be in person on Monday. So thanks so much. Have a good weekend. Reach out with any email questions you might have. I'm very responsive. Okay. Bye-bye.
Thank you. Have a great day.
Same to you.
Thank you.
Thank you.
Thank you, Dr. T.
Bye, Selena. Bye, Sophia. Bye. Thanks, Abraham. Bye, Joey. Bye. I love your positive energy. Deeply. Okay. Bye.